In the time it takes to snap your fingers, the sun releases enough energy to power our entire civilization for 4,500 years. So naturally, scientists and engineers have been working to build a miniature star here on Earth to plug into our power grid. And the thing is, we already kind of have. It just doesn't look like a tiny star floating in a lab. Stars are made of an almost incomprehensible number of particles which gravity compresses into a super dense core. This core is hot and dense enough to force atomic nuclei together, forming larger, heavier nuclei in a process known as fusion. The reverse process, where one atom splits into two, is called fission. In both processes, the mass of the end products is slightly less than the mass of the initial atoms. But that lost mass doesn't disappear. It's converted to energy according to Einstein's famous equation. And since c squared is such a massive number, both fission and fusion generate a lot of energy. Fusion in our sun mostly produces helium nuclei. In the most common pathway, two protons fuse to form a deuterium nucleus, which then fuses with another proton to form a helium-3 nucleus, which then fuses with another helium-3 nucleus to form a helium-4 nucleus. But there's a catch. That first step is incredibly rare. Only 1 in 100 septillion collisions between protons results in a deuterium nucleus. In the sun, this isn't a problem because there are so many protons that even a reaction this rare happens all the time. But on Earth, researchers rely on a more easily reproducible reaction where a deuterium nucleus fuses with a tritium nucleus to form a helium-4 nucleus and a neutron. We've actually been doing reactions like this one inside particle accelerators since the 1930s. But these accelerators are not designed to harness the energy this reaction releases. Rather, they're used to generate neutrons for a variety of scientific and military purposes. Whereas, if we want to use fusion to produce limitless energy, we need a device that can harness the energy released, channel enough of that energy back into the device to keep the reaction going, and then send the rest out to our power grid. And for that job, we need a nuclear fusion reactor. Like a particle accelerator, a reactor would generate helium nuclei and neutrons. But that reaction would happen in a super hot core, and the resulting neutrons would shoot outward to heat up a layer of lithium metal. That heat would then boil water, generating steam to run turbines and produce electricity. Meanwhile, the helium nuclei would stay in the core and slam into other nuclei to keep the reaction going and the electricity flowing. This tech has many practical challenges, including how to confine a swirling mass of million-degree matter. But the biggest hurdle is achieving what's called ignition. An energy technology is only commercially viable if it puts out more energy than it uses, and a fusion reactor needs a lot of energy to get the core hot enough for fusion to occur. So there's a tipping point, a moment when the fuel is hot enough to start the reaction and release more energy than is needed to reach and maintain that temperature. This is ignition. Stars reach ignition under the force of huge amounts of gravity, but this approach is impossible on Earth since you'd need thousands of times the mass of, well, the entire Earth. So researchers typically rely on vast arrays of lasers or methods that combine magnets with high-energy particles or electromagnetic waves similar to those in your microwave oven. In 2022, scientists at the U.S. National Ignition Facility demonstrated ignition for the first time ever, using 192 lasers to heat deuterium and tritium to 100 million degrees. While this was a huge step forward, we're still a ways off from a self-sustaining, long-running reactor that produces more energy than it uses. But once operational, these relatively small reactors could power a city of 1 million people for a year with just 2 pickup trucks of fuel. Today, you'd have to burn roughly 3 million tons of coal to produce that much energy. That is the promise of fusion. Limitless, on-demand energy with almost no emissions. True star power, right here on Earth. In the meantime, should we be making better use of the star power we already have at our disposal? Dig into the cost benefits of switching to solar with this video. And to learn about impactful steps you can take to combat climate change, check out ed.ted.com/earthschool.